Okay, welcome back everyone. In this video we're going to talk about sound waves. So we're going to start discussing a very particular type of wave. So we'll start with the definition, and sound waves are basically regions of low and high pressure. And this low pressure is sometimes called a rarefaction. Squeeze that in there. And the high pressure regions are called condensations. Now, sound waves are a little bit different from what you might think about for a normal wave. Like if you took a slinky and shook it up and down, the wave would go side to side, and it might look something like this. But a sound wave is actually a longitudinal wave. And remember from a previous video that this means that the particles of the medium are going to vibrate parallel to the wave motion. And I have a nifty little simulator that shows us this. Okay, so we'll be experimenting with this a little bit later. And so this is showing the sound being emitted by a speaker as regions of low and high pressure. So the low pressure is the darker region and the higher pressure is the lighter. So you can see that if I move my little sensor to any point, it'll mess up the graph temporarily, but then over a long period of time, well, there's your cosine wave again. But instead of measuring amplitude, we're dealing with pressure. Okay, now it's kind of weird to think about, well, what is it in the air that's actually vibrating back and forth? So if I change it to a particle viewpoint, get that out of the way, we're actually dealing with particles. And so some of them are marked in X, but first watch just as a whole, you can see the waves kind of traveling through the air. And this is a greatly slowed down version. Most sound waves that we can hear have a much higher frequency than this, which looks like about one wave every 2 seconds. Okay, now the important thing is keep an eye on a particle marked with an X, like maybe this guy right here, if you can see my pointer. And watch and look what happens to its motion. You have to watch it for a long period of time. And so what you can see is that it's actually executing kind of a narrow elliptical shape. So that's really what's happening with a longitudinal wave like sound. And just keep in mind that this is a 2D view, but in real life it's a three-dimensional wave that expands spherically. So this thing basically is traveling in a little circle back and forth. Okay, so we'll talk about a couple of properties of sound waves. And one thing is that even though sound waves are regions of low pressure and high pressure and are mainly longitudinal, transverse sound waves can, let me not get ahead of myself here, transverse sound waves can travel through solids. And a great example of this is just put your ear down on your desk right now and knock on your table. You should be able to hear it. And that's because the particles in the solid are vibrating and transmitting the sound. So I have a neat little demo I'll show you in class with a tuning fork that kind of displays the same thing. So most people will hear anywhere between 20 Hertz to 20,000 Hertz in terms of frequency, and this depends on your age, and we'll talk about in class really what happens as you get older and you lose that upper end of the hearing range. Now, lower than 20 Hertz is what we call infrasonic, and actually it's been shown that tornadoes produce infrasonic sound, as can elephants. elephants are actually good at hearing infrasonic, and pigeons can actually hear things with as low a frequency of about 1 hertz. And I can write pigeons. Let's try it again. All right. Okay, and there's also sound waves that are higher frequency, and that's ultrasonic. So when you hear about an ultrasound, that's basically what ultrasonic means. This is more than 20,000. And so again, less than 20 and more than 20,000. And what we'll talk about later on is the fact that ultrasounds work because when sound waves reach a boundary between two media, just like in our Slinky lab, they will reflect and flip upside down depending on density. And so in this way you can get a good sense of what kind of material you're sending waves towards based on what comes back. So ultrasonic, we're talking about an actual ultrasound, which is kind of named after it. And it's used in sonar, so finding out how deep the ocean floor is, etc. Bats use this for echolocation, amongst other things. So there's a lot of applications of ultrasonic. And finally, the last thing we'll talk about is the speed of sound. And the speed of sound turns out to be somewhere along the lines of 331 meters per second. And this is in air, and this is room temperature, I believe. Actually, I lied. That's at 0 Celsius. But if it's warmer than that, then you add 0.6 meters per second for every degree Celsius. So for example, room temperature means that you've got 343, and so on and so forth. So the speed of sound really does depend on the temperature, and I want you to try to think about, well, why is it linear, and why does the speed of sound increase when the temperature is greater? So that's one of the things that we'll talk about in class. But that's it for this intro. We'll see you next time.